Number 10, detecting gypsy moths. The gypsy moth is a serious threat to oak and aspen trees. A state agriculture department places traps throughout the state to detect these moths. When the traps are checked periodically, the mean or average number of moths trapped is only 0.5, meaning half of a moth. Okay, but some traps have several moths. The distribution of moth counts is finite and strongly skewed with a standard deviation of 0.7. What are the mean and standard deviation of the average number of moths X bar in the 50 traps? Okay, so let's talk about this for a second. In the previous problems we looked at, we were given that our initial distribution was normal. So our sample size wasn't of a super concern to us because if your initial distribution is normal, your sampling distribution will also be normal without any concern. If your initial distribution is skewed, then you need to make sure that you have a large enough sample size so that you can, the central limit theorem kicks in and we can use this normal distribution. So for the central limit theorem to kick in, we need a sample size of 30 or larger. In this case, we have a sample size of 50. So the central limit theorem kicks in and we're good to go here. But our mean is still going to be the same, so it's still 0.5. And our standard deviation is going to be 0.7 divided by the square root of 50. Okay, and when I did that in a calculator, I got that that was approximately 0.598. Okay, and so with the central limit theorem, it's going to give us a distribution that is normal, 0.5, comma 0.598. Okay, and we're looking for the probability that the average number of moths is, in those 50 traps is greater than 0.6. So that probability, when I put that into our probability calculator, I got 0.4336. We can go ahead and take a look at that. Okay, so my mean was 0.5. And my standard deviation was 0.598. Okay, I'll click scale to fit. And I'll activate that first row, and I'm looking for the probability greater than 0.6. Okay, so right now it's set at less than 0.6, so I'll click the inequality sign to flip it over, and there's my 43.36% that I got. All right. Okay, I would like you to try number 11, boron insurance, and number 12, hospital length on your own. So go ahead and pause the video and try those problems out on your own. Okay, so let's go ahead and give those a try, see if we came up with the same answers. All right, so for this insurance one, I have a distribution that is normal with the mean of 125 and a standard deviation that is 300 divided by the square root of the 10,000 policies they're wanting to sell. So that gives me a normal 125, comma 3. Okay, and then that means my probability here is going to be 0.0004 or 0.04%. So that's 4/100th of a percent. Okay, so I would say the company probably can pretty safely sell those policies at $135. And that should be a pretty safe thing to do. On number 12, so you notice that this one doesn't say that it is normally distributed there. So when they ask us about the distribution of this single patient, that's going to cause a problem. So I'm going to put a note here that the original distribution, or these stays, these length of stays, are normally distributed. Otherwise, we're going to run into some issues here. Okay. And so you can do the same thing with number 14 when we get down to that one on the classwork too. It's safe to assume that those lengths of those fishes are normally distributed as well. Okay, so for a single patient, we're going to have that this is normally distributed, 9,3, because we would just be divided by the square root of 1. Okay. My probability that the length of stay is less than 9.6 days is 0.5793, okay, or 57.93%. And if we go for a sample of 100 patients, now my distribution is going to be normal with a mean of 9. My standard deviation is now 3 divided by the square root of 100. So that gives me normal 9, 0.3 for my standard deviation. And now when I calculate that probability that the stay for this group, this average stay is going to be less than the 9.6 days, I get 0.9772. So 97.72% of the time, the average stay for these 100 patients is going to be less than 9.6 days. So if you feel really solid about this, feel free to stop the video and move on to the next one. If not, I'm going to go through the tech part of this so you can see how this is all worked out. Okay, so for the tech part for the Moron Insurance, our distribution was normal with a mean of 125 and a standard deviation of 3. So I'll click Scale to Fit. And then I'm interested in the probability that it's going to be greater than. So I'll flip that inequality, $135. Our average loss will be no more than 135. And so here's where I get that 0.0004. Okay, so hopefully that makes sense. Then number 12 for the hospital stays, I had a mean of 9. Okay, and then a standard deviation of 3. And I'm looking for the probability that a length of stay will be less than 9.6. So I'll flip the inequality back to less than, and I'll put 9.6 in. And hit enter. So there's my probability is less than 5. My probability that it's less than the 9.6 is 0.5793. And then if I look at a sample of 100 patients, and I'm wanting to know if their average stay, the probability of their average stay is less than 9.6. The thing that changes comparing a single patient to the average for the 100 patients is just that standard deviation. So that standard deviation gets divided by the square root of my sample size, so by the square root of 100, so it changes to 0.3. I'll click Scale to Fit, and now my probability changes to that 0.9772. Right, so hopefully that makes sense, but if not, feel free to shoot me an email or come to office hours on Zoom.